Section 2.6, Rational Functions, Day 1. The goals of this lesson: students will be able to sketch the graph of simple rational functions, identify the domain, range, asymptotes, and intercepts of simple rational functions. A rational function has the form r of x equals p of x divided by q of x, where p of x and q of x are polynomials, and q of x does not equal 0. In fact, the definition of a rational function is a ratio of two polynomials. The parent function for a rational function is 1 over x. This is a graph of a hyperbola. And hyperbolas have the feature of having asymptotes. An asymptote is a straight line that a graph approaches as the variables in the equation approach infinity. We'll explore asymptotes a lot during this lesson. This slide explores the parent function y equals 1 of x, which is represented by this graph. You can notice by the graph that there is a vertical asymptote at x equals 0. The graph approaches the line x equals 0 from the left side and the right side. That's the equation of the vertical asymptote, which is x equals 0. The horizontal asymptote is y equals 0. In this case, it's the x-axis, y equals 0. Notice as the graph gets very large or gets very small, it's approaching the line y equals 0. The domain is all real numbers except for 0. The range is all real numbers except for 0. In this particular rational function, there is no x-intercept and no y-intercept. The general form of a simple rational function is given as y equals a divided by x minus h plus k. To find the vertical asymptote, you always take what's in the denominator and you set it equal to 0. So x minus h equals 0, because that's what x cannot be. When you solve for x, you get x equals h. So the vertical asymptote of a simple rational function is x equals h. You can see the vertical asymptote on the graph right here. Now, the horizontal asymptote is a little different. For the horizontal asymptote, you want to look at the behavior as x gets really large. So think of this x value as being huge. Huge meaning like 1,000, 10,000, a million. If you take a small number and divide it by a huge number, and then you minus another small number, you basically get 5 divided by 5 million, which is really close to 0. So this term really becomes 0. And then you're adding k. So what happens with the horizontal asymptote is as x gets really large, y approaches k. So the horizontal asymptote is y equals k. You can see it represented over here by the graph. We will now do the example graph y equals 4 over x. This is a very simple rational function. The first thing you want to do is set the denominator equal to 0. So in this case, our vertical asymptote is x equals 0. We will dot the vertical asymptote over here, which is the y-axis. Now we need to find the horizontal asymptote. Since there is nothing added here, our horizontal asymptote is y equals 0, which we will dot on the x-axis. Now our domain is all real numbers except for 0. So x does not equal 0. And our range is all real numbers except for 0. So y does not equal 0. In this particular equation, there is no x-intercept and no y-intercept, because our axes are in fact the asymptotes. So none and none. To just figure out our points, we're always going to graph points around our asymptote. So since our asymptote is 0, which is undefined, we're going to graph points around it. So I'm going to graph -1, -2, and -4, and 1 and 2 and +4. So when we fill in this table, which I would encourage you to do using your calculator, I would put the equation 4 divided by x into your calculator. You end up with these as your following points. This is 4, this is 2, this is 1, and this is -4, -2, and -1. So we have -4, -1, -2, and -1, -4, 1, 2, 3, 4. That's one branch of our hyperbola. And then we'll graph the other side, which is 1, 2, 3, 4. The other branch of the hyperbola. This is the graph of the equation y equals 4 divided by x. Now we're going to graph y equals -3 divided by x minus 1 plus 2. This is still a simple rational function, but it has more interesting vertical and horizontal asymptotes. We first start by taking the denominator and setting it equal to 0. So x minus 1 equals 0. So our vertical asymptote is x equals 1. Our horizontal asymptote is the k value, because remember, we're looking at -3 divided by a huge number, minus 1 plus 2. This becomes 0, and our horizontal asymptote is just y equals 2. The domain is always everything but the vertical asymptotes. So in this situation, our domain is x does not equal 1. The range for simple rational functions is everything but the horizontal asymptote. So in this case, y does not equal 2. The x and the y-intercept, x-intercept is always found by setting y equal to 0 and solving for x. So 0 equals -3 over x minus 2 plus 2. When we move the 2 over, we have -2 equals -3 over x minus 1. Now we can multiply both sides by x minus 1. So we get -2 times x minus 1 equals -3. We can divide by -2. So we have x minus 1 equals 3/2. And we can add 1. So x equals 2.5. So our x-intercept in this situation is 2.5, 0. The y-intercept we can find by setting y equal to 0. So we have not y equals to 0, sorry, x equal to 0. -3 divided by 0 minus 1 plus 2, which is -3 over -1 plus 2, which is +3 plus 2, which is 5. So our y-intercept is 0, 5. The nice thing is we now have 2 points already for our graph in terms of graphing our simple rational function. So once again, we're going to graph points around the asymptote. So since we already have our y-intercept as 0, 5, we'll also graph -1, and we already have 2.5, 0. So let's also graph 3. I'm just going to use the table button on my calculator and find these points. So -1 is 3.5, and 3 is 0.5. You could use different points. We could also use maybe 4, 1. Maybe having a third point would be nice. So now I'm going to dot my asymptotes. So my horizontal asymptote is y equals 2. And my vertical asymptote is x equals 1. We're going to plot our points. So we have -1, 3.5, 0, 0, 5. So this branch looks something like this. And the other side, we have 2.50, which is our x-intercept. We have 3.5, and I also added 4, 1 to make it a little bit easier. So there's our other branch. Now it's really important that you draw your hyperbola so it goes close to the asymptote, but it doesn't really touch it, as I have outlined. And you should always dot your asymptotes. For our last example, we're going to graph a simple rational function, but it's in a different form. Notice how there's no plus k over here. When there's no plus k over here, like that, what you have to do is a little bit tricky for the horizontal asymptote. For the vertical asymptote, it is the same situation. So we're going to start by looking at our vertical asymptote. So x plus 2 equals 0. So x equals -2. Now in this form, think about what we talked about earlier about x being really large. If you have 3 times a huge number minus 6 over our huge number plus 2. As x gets really, really large, so 3 million minus 6 over 3 million plus 2, these numbers are really going to be very small. So what you're going to be left with is 3 times a huge number divided by a huge number. And if you look about this, our huge numbers can cancel out, and we're just left with 3. So our horizontal asymptote in this situation is y equals 3. We'll talk more about these particular types of rational functions tomorrow. The domain is the same situation. So the domain is everything but the vertical asymptote. So in this case, x does not equal -2. And the range is everything but the horizontal asymptote. In this case, y does not equal 3. Our x-intercept we find by setting y equal to 0. So 0 equals 3x minus 6 divided by x plus 2. When you multiply both sides by x plus 2, what you find out is 0 times x plus 2 is just 0. So our x-intercept is really just when 3x minus 6 equals 0, which happens when x equals 2. So our x-intercept is 2, 0. Our y-intercept is found by setting x equal to 0. So y equals 3 times 0 minus 6 over 0 plus 2. So we have -6 over 2, -3. So our y-intercept is 0, -3. So now we can create our table. So once again, we already have a few values for our table. We know our vertical asymptote is -2. So that's undefined. We have our y-intercept, which is 0, -3. And we have our x-intercept, which is 2, 0. Both of those points are on one side of the asymptote. So we need points on the other side of the asymptote. Once again, put it into your calculator and find those points. It's really important when you put it into your calculator that you remember to put parentheses around the numerator and parentheses around the denominator so that your calculator does the proper order of operations. So in this situation, we'll do -5, 7 and -6, 6. I could have chosen any points for my calculator, but these are the ones that fit the graph nicely with what I already have. So I'm going to dot my asymptotes. So here's x equals -2. And I'm going to dot my horizontal asymptote, which was y equals 3. And I'll graph my two x and y intercepts. So I have 0, -3, and I have 2, 0. So this branch of my hyperbola looks something like this. And on the other side, I have -6, 6. And I have -5, 7. So this branch of my hyperbola looks something like this. Once again, when sketching it, be sure it approaches the asymptote, but doesn't touch it.